None shall pass.
What?
None shall pass.
I have no quarrel with you, good Sir Knight, but I must cross this bridge.
Then you shall die. I move for no man.
You know, that type of attitude will never win you customers. Before we begin the video, a quick public service announcement. The demonstration in this video was performed on the Cisco Viral platform. In the description box, you can find the Viral file, complete with the initial configurations of all the devices. You can download this file and follow along with the steps performed in the video. Welcome back to the BGP Security series. We continue on the topic of Flowspec today with a live demo on iOS XE, XR, and Junos devices. Let's begin. So before we get to any of the actual Flowspec scenarios, we must understand the topology, the infrastructure we'll be performing this demo on. So here's a quick look at the topology. Now, the most important thing that is probably on everybody's mind, which device is which flavor, right? So in this case, all of the devices, other than the two that I'm just going to point out now, every device is either running iOS or iOS XE. Those are the only two flavors that are running on majority of the devices, except the two that I'm about to show. And both of those also run the same command set, so really there is no difference between them. But the two devices that are different are the iOS XR device up here, this one, and so this is an XRV device to be exact, without an actual line card. So this is just a control plane, no line card, and a VMX device that is fully virtualized control plane and a fully virtualized forwarding plane. So that actually supports most of Flowspec. The iOS XR device, if you look at it, it's really not in the data plane. The reason it's not in the data plane is the XRV device does not really support the data plane functionality of Flowspec unless until you provided a line card. In this case, we don't have a line card. So what we are doing with this device is it's serving the role of a route reflector as well as a controller. So this is going to be a Flowspec controller, and it's going to be a route reflector that makes it convenient. For BGP, by the way, so route reflector for BGP. With the VMX device, I both have a virtualized control plane and a virtualized forwarding plane. So this thing is doing everything. It is in the data plane, and it can also act as a controller if need be, and it'll do both of those things. So VMX, XRV, both of those devices are here. And finally, all of the iOS devices, they have one basically drawback. They cannot be a Flowspec controller. So whenever they are being used in this particular Flowspec, you would always see them as filtering devices and not as policy creating or control devices. You cannot create a policy on them. Now a quick look at the various ASs. The major part here, the SP if it were, is AS1. And AS1 runs both IPv4 and IPv6. It's providing IPv4 services as IPv4 plus MPLS and V6 services as 6PE. So there's either VPNv6 or 6PE. The core is essentially IPv6 free, but it really doesn't matter. On the edges, we have full functionality, and we also support IPv6 in the core with the use of 6PE. The ASBRs, that is R2 and VMX3, they are also connected to what is our pseudo internet via iNet7 router, which is in AS7, and they get both IPv4 and V6 routes. And to the far left of the iNet router, you have AS200 that has our proverbial good guy, and AS201 that has the proverbial bad guy. And their IP addresses sort of reflect that. It's 200/8 and 201/8, and those are the addresses that we are going to be concentrating on. Now, the customers, or essentially the devices that are going to play the victims here, they are going to be on the far right of the topology. Now, in the global routing table, you have AS8 with CE8 in it. So that is using the SP as an ISP or an internet service provider. So that sends its traffic out to the internet. It is also therefore exposed to all of the devices on the internet. So you can imagine that flow spec for CE8 is going to be IPv4 and IPv6 flow spec. And then finally, we have a VPN customer, which is in VPN A. We are calling it customer 1. And that has two devices. There's customer 1 CE9 and customer 1 CE10. And they get their services from PE4 and PE6 respectively. So the traffic flowing to those devices is VRF only traffic. So you can imagine it's going to support your VPNv4 and VPNv6 flow spec. But as for the topology, that's all that we need to concentrate on. Now that we've taken care of the topology overview, the first task at hand then is IPv4 and IPv6 flow spec implementation. So FlowSpec is largely based on BGP. In fact, it's totally based on BGP. And before we can even write the policies or deploy the policies, the first thing we have to assure is that the BGP FlowSpec sessions are then created between all of the devices. So first up, we're just going to create IPv4 and IPv6 BGP FlowSpec sessions, leaving VPNv4 and VPNv6 for a separate topic. So in this case, iOS XR, XR1 or XRV1 is the route reflector. So that would have to then be changed for all of these devices. Currently it runs VPNv4, VPNv6, IPv4 and IPv6. So taking a quick look at XR1, we can see that it's running all four of those families. It runs IPv4, IPv6, VPNv4, VPNv6, and then depending on the neighbor, you may have all four of those families or some of those families, right? So it really depends on whether the neighbor requires VPN services or not. So pretty much IPv4 and IPv6 though are everywhere. So the first thing we'd have to do here is go into router BGP and start those families, right? So make sure that BGP knows to run both of those families. The command set here is pretty simple. Address family IPv4 FlowSpec and address family IPv6 FlowSpec. So once those two families have been started, now we need to activate them under the neighbors. So in this case, all four of the neighbors other than maybe PE6, they all require those families to be activated. PE6, at least on our diagram, only has VPN customers, but we'll just make sure that they are running for every single one of the devices. So I'll show it for one of the devices, pause the video, and then finish the other devices. How you would do that is, again, go to router BGP1, pick out the neighbor. So in this case, I'm going to start with the lowest neighbor, which is neighbor 2. And I will copy basically whatever is under the other two families. So it has to be a route reflector client. That's the only need here. So I would say address family IPv4 FlowSpec, route reflector client, and address family IPv6 FlowSpec, route reflector client. So having done this, now I'll finish the other four neighbors while the video is paused. And now on your screen, you see we have configured neighbors 3, 4, and 6 similarly. So those are all of the neighbors, and that's basically all you need to do to enable the BGP address family FlowSpec or IPv4 and IPv6 FlowSpec exchange between the devices. I'm going to commit this configuration. And that's not going to make any changes yet because the other devices don't support those families yet. So starting from router 2, which happens to be an iOS device, and you can see the BGP neighbor relationship bounce because the capabilities change from one side. So now we'd have to ensure that this device also supports BGP FlowSpec, as we will with all of the other devices. So let's look at the current configuration. And in this current configuration, you see we only have address family IPv4 and IPv6. So we'll go ahead and we'll change that. So router BGP1, we'll say address family IPv4 Flowspec, and we will activate just the internal BGP peer. So the external BGP peer we will not check. We will not do that. And for IPv6, this device is sort of an experimental device which used to have a tunnel with the original route reflector. But what we need to do actually is also fix the IPv6 on it. So if you're following along on your configurations, this is probably going to be wrong on your initial configurations as well. So you may want to change this there as well. And what we would need to do is enable 6PE. And the additional command you would need here is the send label command for BGP IPv6 labeled unicast. But that's only fixing IPv6. So now we get to IPv4 Flowspec, which we may have already done. So we have. And we'll do address family IPv6 Flowspec. And it would be the same two commands. The neighbor has to be activated. You have to make sure that the community is being sent. And once this relationship comes back up, which it should shortly, the command you should use to verify is show BGP IPv4 Flowspec summary. So if you don't see an active or an idle here, you're good to go. You're exchanging that family. Similarly for IPv6. Now I'll pause the video while I'll make the same changes on PE4 and PE6, but it's exactly the same command set. So what I've done is I have made the same changes on PE4 and PE6, and just as a proof, on the route reflector, now we are using the commands for verification of IPv4 and IPv6 Flowspec. You can see all the devices except 3333, which is VMX3, they're all now exchanging this family. So the only thing now left is to go to VMX3, which is a Junos device, and also configure that for the exchange of IPv4 and IPv6 Flowspec. So let's go ahead and configure this. Show protocol BGP to get the current configuration. And as you can see, it's a little bit more scalable here. I have an internal BGP group. I have the... Well, actually, this is not really working yet because this neighbor really needs to be changed. So again, if in your initial configs, you might find that there is a little hang up with this one. But what you have to do then is to change the neighbor to 6666. And I believe you can actually do that with the rename command here. So rename protocol BGP group GPI BGP. And then the neighbor is going to change from 6666 to neighbor 1111 because that's our new route reflector. So let's go ahead and commit this. And what I'll do is I'll make sure that this change carried, this change is correct on XR1. So if I say do show BGP IPv4 unicast summary, I still see that as idle. But now it's exchanging information, it's open confirm, and now it's actually receiving prefixes. So that was a good catch there. And essentially what we did was we had the wrong route reflector address on it. It was from a previous configuration, but if you change this on your initial config, your show protocol BGP would then look like this, which is good. It's doing 6PE and it's doing regular IPv4 prefix exchanges. So now within the same group, so edit protocols BGP, and then the group is going to be group IBGP, and the neighbor inside that group is going to be 1111. What you need to do here is you need to set family INET Flowspec and set family INET6 Flowspec, or rather show compare. So that's all we've added. We've added the flow SAFI. Technically, we've only added the flow SAFI to the INET and INET6 AFIs. So I'm going to commit this config. And once it's committed, what I should see on XR1, once the flaps happen, is the IPv4 Flowspec summary should go through the same motion. So it should go from idle to open confirm. There we go. And similarly, IPv6 should go through that. So you can see it's no longer idle, and then IPv4 one last time is no longer idle. That means our infrastructure now is exchanging address families IPv4 flow spec and address family IPv6 flow spec with the route reflector. And that brings us to the end of subtask 1. The next thing we're going to do is iOS XR as a controller which feeds the flow spec NLRIs into our network. So in order to use iOS XR as the controller, we first need to think of a policy, right? What would be a policy that we would define that would need to be implemented? So in our case, we have basically decided that we are always going to try to stop Mr. Bad Guy in AS201 from hitting any of the victims in the customer networks. So the victim right now for global IPv4 and IPv6 are both the addresses that are on CE8. So it's 8888 and then 2001:8:8. So both of those bad guy should not be able to get to, but good guy should be able to get to. The policies should be granular enough. And we're not going to stop pings because I want to just leave them on as a testing tool that sort of verifies that FlowSpec is doing its job. But we instead would like to stop an actual application protocol. So for example, we would like to stop telnet. So again, we're going to use pings as a connectivity tool test or test tool, and then the telnet would be the application that we are trying to stop. So from good guy first, let's go ahead and ping 8888 and we'll source it off of the loopback. So that's successful. How about telnet? 8888 and then the source interface is going to be LO0. In this case, the connection is coming refused by the remote host, but this is probably actually being refused from the router itself because it's not been configured for telnet. So once again, in initial configuration, it probably is not included. What we need to do here is go to line VTY 04, so maybe just 4 lines. Transport, we'll leave it wide open, right? So we'll say transport input all. So it's just accepting all of the protocols, SSH, RLogin, telnet, etc., etc., etc. And then we'll set a password on it. We'll just say password Cisco. This is like the least secure configuration that you could put on here. Let's see if this makes any difference. So now it's open. We say password Cisco, and there we go. We are in CE8. Bad guy 201. Want to do something similar here? We'll say ping 8888. And I just didn't source it from the right address, so I'll say source loopback 0. So it can reach there. And how about telnet? 8888/source interface loopback 0. And similarly, once we enter the password Cisco, just in case, I just said it. So we are in CE8. So that's a rudimentary test of IPv4. We are similarly going to test IPv6. So we'll say ping 2001:8:8, source loopback 0, or actually source has to be set here. So this would be 200:200. And that's successful. How about telnet? 8:8. And here I can actually select an interface. So I'll say source interface loopback 0. And there we go. So it's opened up the console. And if I say who, then I can actually see that there is a telnet connection from Mr. Good Guy, and then an IPv6 connection from Mr. Good Guy, and an IPv4 connection from Mr. Bad Guy. And let's exit out of Mr. Bad Guy to test the same thing here. We'll say ping 2001:8:8, source 2001:10:, actually it's 201:201. So pings are good. And then we'll test the telnet 2001:8:8, source interfaces loopback 0. And both of the IPv6 addresses work as well. So our 6PE is functional. Our everything is pretty much wide open. So now what do we want to do from a policy point of view? So the first thing I think I'd like to do is literally just stop telnet. So maybe stop telnet while keeping SSH open or something like that. Furthermore, we want to let good guy still have access to CE8, but probably not the bad guy, right? So we'll have a source address, we'll have a destination address, and in case of, at the very least, Cisco is on record saying this, that the Cisco routers only do Flowspec on Ingress. So whenever you think about the directionality of the traffic, think about it entering into your system, so Ingress traffic. And that also, at least for VPNv4 and VPNv6, I've seen that it's not applicable from the MPLS core. So MPLS core is not being treated as an Ingress interface. VMX pretty much does the same thing, so as long as you keep the policies in mind that way, it is also at least doing it on the Ingress traffic. So in this case, let's say the source IP needs to be, I'm just going to say 201. So that also means IPv6 201 and IPv4 201. We'll do those separately, IPv4 first. The destination IP can be selected as well. So let's say it's going to be 888/24. So let's just restrict the whole /24. And then we can pick a port. And the port I'll pick as 23 for the telnet. So this policy has to be described. This is going to be the capture part of the ACL. This is what you're going to match up against. And then there needs to be an action. So that action, in our case, it's easiest to just demonstrate drop, right? So policing, etc., becomes pretty complex to demonstrate in a lab. But you can police the traffic down. You can limit the bandwidth. You could inject it into another VRF, watch the previous video for all of those. But in this lab, we're going to keep it simple. We'll just keep the action drop. So all of that has to be defined on XR1. How do we do it? Well, essentially what we do is we define a policy map. So in that policy map, we're going to have several class maps that match up against different traffic. And then we'll apply that policy map in a particular part of the configuration called the flow spec, and that's going to define your policy. Now this policy map needs a class map, and that class map, so policy map itself is of a special type, but the class map is also a special type. So you'll have to say class map type traffic, because this is specially created for flow spec. So class map that type traffic, it has to be match all, because we have a lot of different match criteria here, right? We need that particular source IP, we need that particular destination IP, and we need that destination port. So as you can see, it is a match all type of scenario, so use match all for it. In this case, let's say CM IPv4 telnet. I'm just giving it a random name. You can give it whatever name that you want. Now, in that class map, we're going to match on different criteria. We know of at least 3 that we want to match again. So we'll say match, and here are all the criteria available to you. We are interested in source address. And we're only going to scratch the surface when it comes to policy making. I'm more interested in showing you the whole mechanics of it, but you can really go wild with the policies if you want to. So match source address, IPv4, and in that source address IPv4, we want to match the bad guy address, right? So it'll be 201.201.201/32. So that's the source address. We're also going to match the destination address, IPv4, and this is going to be 8880/24 because we want to block the entire /24. And finally, we want to match the destination port. So we'll say match destination port, and we'll just block 23. You could have multiple ports in here if you want to, if they're in the same list, same exact line. It's pretty much an OR-based scenario because a packet can only have one destination port. You could furthermore match the protocol if you want. So you could say match protocol TCP, and that way the policy is a little bit more robust, it's a little bit more tight. But that's your class map. So show And that's the class map right there. It's type traffic, it's named something, and then it has all of this criteria in there. So this is used to match the traffic. Now in the policy map, we will decide the action that we need to take on the matched traffic. So like I said, that policy map itself is of a special type, and this time it is PBR, type PBR. And you can just give it some name. So we'll say PM IPv4 traffic. Now you can have multiple policy maps. So it's not like a QoS policy that it would only allow you one policy map. You can have multiple policy maps that you can have for different things. So either you can have multiple classes inside a policy map, or you could have multiple policy maps with separate classes. How you scale that is entirely up to you. I would say that read Cisco's recommendations on that. But policy map, type PBR. In this, we need class, type traffic, and then CM IPv4 telnet. Now, not all of these actions are available to you, but at the very least, the drop action is. So you can police it to 0, or you could drop. It's exactly the same thing. The community essentially carries a bit rate. For drop, that bit rate is all the way down to 0. So drop, I'll say exit and show. And here it is. Here's that complete policy that we see up here manifested in a policy map. Let's commit this config. And it took, so there's no problem there. Finally, we need to apply this policy map under the flow spec hierarchy. So we'll say flow spec address family IPv4. Now this is the global address family, which the VRF keyword should have given it away. But address family IPv4, and what we are doing is we are implementing a service policy type PBR, and the name of the policy is PM IPv4. And like I said, you can have multiples of these service policy commands in here. So you could either scale with policy maps, or you could scale with class maps inside those policy maps. That's entirely up to you. Next thing we need to do here is commit. And once we commit this policy, what we should see then is a BGP NLRI that has been created out of this. Let's go ahead and check that first. So we'll say do show BGP IPv4 flow spec. And there we go. We have a destination, we have a source, and this is one long NLRI. We have a protocol defined, protocol 6, which happens to be TCP. And finally, we have a destination port and a prefix length, because all BGP NLRIs have a prefix length. Now, we cannot see the action here because I'm not looking at the details of this. And I believe you cannot see the details anyway on XR, but you should be able to just take this whole thing and do the command on that. And there you go. In this, you have an extended community, which is Flowspec. It carries the traffic rate, and that traffic rate happens to be... There is a way of reading this, but I believe that traffic rate right now is 0. So that essentially tells the devices that receive the traffic to drop it. There's another friendlier way of looking at this. You could say do show Flowspec IPv4 detail. And that should show you this in a little bit more legible manner. So destination, source, similar things. But the traffic rate, as you can see, is 0 bits per second. So that's the action taken on here. Now, what should have happened is BGP should have already carried this. Number one, we are originating it on XR1. It is also a route reflector anyway. But since we are originating it on XR, there's no question that it should have propagated to the rest of the network. Let's check a couple of devices for that. So we'll check R2, do show BGP IPv4 flow spec, and there's that NLRI. We'll check VMX3. The command here is a little bit different. It is run show BGP. Actually, it should be run show route table. And that table should be inet flow. So that's where that's the BGP rib. And there you go. So all of the stuff is in there. If you see details, you can also see the communities. And the communities would be, it is here maybe in verbose. Was it just staring me in the face and I didn't see it? I'm trying to look real hard here. Here's the community. So it was staring me in the face, the traffic rate, and once again, it's the traffic rate itself is 0. So that's the propagation of the route. The next thing is to have that route installed locally as a filter. For VMX, that should happen automatically, but first let's go to iOS. And there's one more thing that we need to do before this command is implemented. So currently, if you look at the flow spec of this, so this is the BGP rib. So think of this as the BGP rib. That doesn't mean that the route was accepted into the routing table. So there is, just like there is a, there's something that corresponds to the BGP rib, there's something that corresponds to our routing table, which is the flow spec table. So looking at the flow spec table, and IPv4, I see that flow spec is not running yet. So the one step that you need to do here on iOS is you need to explicitly configure flow spec, go into the address family, and ensure that you're locally installing the route on all interfaces. So these 3 commands are extremely important before you're going to be able to perform any filtering on iOS devices. Now if I say do show flow spec IPv4, now you can see I'm actually installing the route. And if you look at the detail of it, you can actually even see if I'm matching any packets or not. Now with VMX, this should be happening automatically. So if I say show, and what VMX does is it essentially creates a firewall filter out of it and applies that firewall filter to the relevant interfaces. So if I say run show firewall filter, and this is the name of that filter, Flowspec default filter, but let me just say enter, or actually let me not use that keyword filter at all. So if I say run show firewall, now I'm running this on bare minimum RAM, so just work with me here. It's going to take a little bit of time before that command goes through. But ultimately what we should see is it should be showing that particular firewall filter. But on R2, it was a little bit of an extra step. Actually, it's taking way longer than I imagined, so I'll pause the video till it shows up. And literally as soon as I paused, it showed up. So now you have the same idea here. You have 8888 going to 200, 200, 200, I'm sorry, coming from 201, 201, 201, 201, protocol 6 destination port 23, and then you have the bytes and the packets count. So now $1 million question, is this thing actually working? So for that, what we need to do is we need to first find out how the traffic is actually propagating. And for that, I also need to open up a connection to INET 7. So let me open up that connection, and then we'll see how to send the traffic. We'll test both R2 and VMX3. So here's INET 7. And what we need to see on INET 7 is show BGP IPv4 unicast. And it is right now using multipath. So that's what I was afraid of. It is using multipath, so it's probably it's load balancing the traffic to VMX3 in R2, but for all intents and purposes, good guy should still be good to go. Actually, that is IPv6 anyway. We are only doing IPv4 yet, so let me find the IPv4 command. Good guy seems like he is good to go still. So if I say who, 200, 200, 200, 200 was able to log in. How about bad guy? So bad guy on the IPv4 address is now no longer able to get there. And to see the details of that, we'll again have to see that pesky show and firewall command. But on R2, we can also look at the Flowspec IPv4 detail. It usually updates fairly quickly, so my my hunch is that it is going to VMX3 for right now. So again, pause the video. And here it is. So it is going through VMX3, and VMX3 is now dropping this traffic. Just to see the same configuration or catching the traffic on R2, what I'll do on INET7 is I'll weigh the traffic towards R2. So we'll do router BGP7, address family IPv4 unicast, and I'll say neighbor 20.2.7.2, and I'll raise that weight to 2000 and clear the routes. Do clear BGP IPv4 unicast star soft in. And okay, now the traffic is definitely going towards R2. So let's send some more traffic from bad guy. And this time we should see it being caught on R2. So there we go. Now we are matching some traffic and dropping some traffic on R2. So it is literally just that easy and just that scalable. As long as you lay down the infrastructure correctly, the rest of it just works. Now, I'll admit I've cheated a little bit here, but YouTube is a cutthroat business and we need to keep these videos as short as possible while giving you the most content. So I've gone ahead and I've created the policy which you can pause the video and take a look at it. But essentially it's replicating everything that we did with IPv4 with IPv6 addresses, and it's been applied. So let's go ahead and commit. Once it commits, what I should be able to do is look at do show BGP IPv6 Flowspec. And that policy is right there. So once again, bad guy as the source, the victim as the destination, and protocol TCP23. And it is being propagated to both, hopefully VMX. So we'll have to take a look at it. Run show route table. I always forget this. This is INET6 flow. And there's that policy, and I'll do the firewall command before I move to R2. And we'll say do show BGP IPv6 Flowspec. So there that is. But once again, if I say show Flowspec, do show Flowspec and IPv6. Oh, actually, I think I might have then. So do show run section Flowspec, because I don't think I had activated it. But I could be wrong about that. So I have not activated it. But somehow at least Flowspec is activated. But if I say details. Oh, I know. So before Flowspec was not activated as an instance. But now if I say IPv6 detail, I essentially should not be able to capture any packets here, because for that, again, I need to go to Flowspec, address family IPv6, and do a local install on all interfaces. So you would definitely need that before it actually drops the traffic. So now if I say do show run section Flowspec, you'd actually see that this is the complete configuration that's needed here. So it was showing it in the table, but it was really not implemented. Now here is where there is a little bit of twist in our video, and it's not the good kind of twist. So I did some research on it, and it does not really seem like my particular VMX here actually has the firewall filter that is needed. So it is supposed to be a Flowspec _default _ INET6 dunder Flowspec firewall filter, but it is not. And I have changed the configurations around. I've tried a whole bunch of things here, but I've not been able to get that filter to generate. So you can take a look at the initial configs. You've seen the changes that I've made. And if you spot something, please be sure to leave something in the comments or reach out to me and I'll provide an update to the video. But for right now, not only is the filter not there, I've also been able to verify that this is not cosmetic. So what I've done is on INET7, I have routed the traffic through VMX3 by use of weight. And now when I come from bad guy, if the filter was actually working, we should not have been able to make this connection, but this connection was indeed made. And if I say who, I can see that it is 2001, 201::201 hitting that router, which should not be allowed on port 23, but it is. So yeah, I've not been able to make IPv6 Flowspec work on VMX, but it is working on iOS. So let's go ahead and change this really quickly. We'll take this command off essentially, and we'll put this command for the other neighbor, right? So we're basically doing the opposite of what we were doing before. We are directing the traffic through R2 is what we are doing. Clear it. And let's look at the IPv6 table here. And yeah, so now the traffic is going through R2. So let's see if bad guy can now make that connection. And now bad guy cannot make that connection because R2, there was some traffic there already, but it should be catching more traffic now. So you can see the number went from 4 to 6. So I don't know what the problem is with VMX, but it is definitely not doing IPv6 Flowspec as I had intended it to. It could be a configuration error, or it could be something that, yeah, it has to be a configuration error. But I just don't know how to solve it. There wasn't enough material on the Googles for this particular one. So I'm going to leave it as it is. And that brings us to the end of this scenario. The next scenario here is going to be using Junos as a controller. And with Junos as a controller, it is just a little bit different, as a lot of things are between iOS, XR, iOS, and Junos. But it's not that bad. So it's about the same thing. And what you have to do is, first of all, we have to define an actual policy. So that part hasn't changed, right? So we'll define a flow route, and I'm making quotation marks with my fingers, to describe the traffic that we are trying to control. Now, we're already doing one sort of control from XR, so I don't want to replicate that exact thing. But let's try a different port this time. So what we're going to do on CE8 is we're going to accept telnet on a different port. Right, and how would you do that? Just pick a line VTY, for example, 4, and add it to a rotary group. So I'll say rotary 1. And what that should do is it should activate telnet on port 3001. So, right, 3000 plus the rotary number. So let's try this. Just from the same host, I'll say do telnet 8888 and on port 3001. So as you can see, that port is now open. So we'll essentially stop traffic to this port now instead of any other port. So from bad guy 201, if I say telnet 8888, source interface should be LO0, and then port is 3001. Right now or maybe the order is different here. So 8888, 3001, and then source interface loopback 0. As you can see, this is open, and this is the traffic we'll stop with the Junos controller. So to that extent, first we have to define the route. Now that route would be defined under routing options, or set routing options, the flow substructure, and then a flow route. So this is what you're describing. Now this route, just like we gave a policy map name on iOS XR, you can give any policy name here. I'll just call it FR for flow route. IPv4, let's call it TCP 3001, because that's essentially what we are doing. It's no longer just telnet, it's TCP 3001. And in fact, I'm not going to set it. Let me go into that hierarchy so we can do the rest of the commands a little bit easier. Next is going to be your match statements, right? So let's say edit match to go one level deeper in the hierarchy. And what are we going to match? All of those things, sorry, not all of those things, all of these things can be matched. So we'll say set source. And the source prefix for this particular flow is going to be 201, 201, 201, 201/32. So that should be it. Now, destination. So destination, once again, we'll say 888 0/24. What else do we have? We have protocol, so set protocol TCP, and then set port, and those are some of your common ports there, but our port is 3001. So those are all of the match statements. I'll go up one, and now what do you do with that? So it's standard Junos policy. You have a match, and then you have whatever you want to do with it, and that's with the then command. So set then, and I'll basically just say discard. And once you do discard, essentially you're doing the same thing that you did on iOS. Let's go back to top, and let's do a show compare to take a look at that policy. And that's your actual policy. So there's no class map policy map type of thing here. You basically just define a route. The route has matches, and then it has an action associated with it. So let's go ahead and commit that. And what this should do is this should bring that route in the local inet flow table. So run show route table inet flow 0. And there's that route. But that route is still not in BGP. So with 3001, if I look in BGP, that route is not going to be exported to BGP yet. So on the route reflector, IPv4 flow. And actually, I stand corrected. So I thought that Junos did not do it by default, but it essentially is taking that route and it is distributing it by default. So it's not even that much more complex anymore. What I thought was you actually have to have an export policy defined, but in this case, seems like we don't even need that. You just define the route, and that route is automatically propagated to BGP. So that essentially brings us here on the client. So let's look at an IPv4 route here. And there it is. So that's the route. And what should happen now, because both of these devices, both of our edge devices, R2 over here, and VMX3, since they're both capable of doing IPv4 flow spec, bad guy should not be able to make this connection anymore. And it's not able to. Let's see if we can catch that traffic on R2. And we are. So essentially that traffic is going through R2 right now. But if it was going through VMX3, we should have been able to see that in run show firewall. And that's it, run show firewall. Now, when it comes to IPv6, since it already did not work and it's not that much different on Junos, I'll leave that as a to-do for you guys. And if anybody faces any problem with it, just make a comment and we can discuss that particular thing in the comments. But right now, it's completely functional. Now, I do realize that I actually ended up setting a port and not a destination port, so it's probably catching traffic in both directions. But I want to see if there is an actual port command there as well. So let's take a look at the policy again, which is right here, the match. And if I say set, what I really should have to actually replicate what we had done there was I should have used destination port. But it does work because it is a port. So it's looking at both source and destination ports, which I didn't realize before. So that brings us to the end of IPv4 and IPv6 flow spec. And that brings us to the final part of our demonstration, which is VPNv4 and VPNv6 flow spec. So the first thing that we have to do here is the first thing that we did in IPv4 and IPv6 flow spec, that is to create the BGP sessions. Now we'll try to do this as quickly as possible this time around since we have already seen it one time. So again, on iOS XR, we'll say router BGP 1, address family VPNv4 flow spec, address family VPNv6 flow spec. So that's the address families. Now there are two neighbors that support these families, so we'll activate both of those neighbors. We'll say neighbor 4444, address family VPNv4 flow spec, and then address family VPNv6 flow spec. Similarly for neighbor 6666, v6 flow spec, v4 flow spec, and This is essentially the configuration on the route reflector. Let's go ahead and commit it. I'm going to do it on P4, and as per usual, I'll pause and then finish P6. So here it's going to be address family VPNv4 Flowspec, and we'll activate neighbor 1111. And then address family VPNv6 Flowspec, and then again activate the neighbor. So while this is coming up, no need to pause the video. I'll essentially just take this and I have to activate it on P6. Or router BGP1. And actually neither one of those work. So address family VPNv4 Flowspec, and then neighbor activate, and address family VPNv6 Flowspec, and then neighbor activate. And that should bring up the VPNv4 and VPNv6 Flowspec connections. Let's check them here. Do show BGP VPNv4 Flowspec summary and VPNv6 Flowspec summary. And there you go. All of the neighborships are now up. Now, we're only going to be doing one of these for obvious reasons. Junos just has let us down on IPv6, so before I make another lecture on it, I'll have to go do some digging on this one, but we'll use iOS XR as the controller on this one. Now, for iOS XR as a controller, one thing you must realize is you must have the VRF defined. So the VRF that you're trying to implement Flowspec in, that VRF must be defined on the controller. There's no other way of doing this because we need to tag those routes essentially the same way we tag regular VPNv4 and VPNv6 routes by the use of route targets. So those routes need to be tagged with the route target extended community. And the only way we can do that is to actually define the VRF on the controller. So what I'm going to do is I'm going to look at my current definition of the VRF, which is in on PE4. Let's cheat from here. So do show run VRFA. And all I really need are these route targets. So we are exporting and importing 1:100, and that's all I'm going to do. So on XR1, I'm going to say VRFA, address family IPv4 Flowspec, and then we're going to export route target 1:100, and we're going to import route target 1:100, and we'll commit this config. So that's the bare minimum VRF config that would be needed here. The next thing we need to do is we essentially need to identify what traffic are we going to stop. So in this case, let's just stop CE10 from being attacked, period. So nobody should be able to telnet to CE10. But first, let's verify if CE9 can do that. So telnet, and before that, let me actually start telnet on CE10. So we'll say line VTY04. Transport input all, and password Cisco. So the minimal config needed. And then we'll say telnet 10.10.10.10 source loopback 0. And again, this is going to be source interface loopback 0, Cisco. And when I do that who command, I can see that 9999 has logged in. So this is the connection that we're going to stop for everything. So we won't specify a source address this time, just a destination address and a port. And once again, remember, it's going to be done on Ingress. So essentially, it will be done here. So that's what we're going to do. So for this, let's once again create a class map, type traffic, because now we know. And this time I'll call it CM-VPN-v4 telnet. And in this, I'll say match destination address IPv4 for 10.10.10/32. Match destination port 23, and then match destination protocol, or sorry, just match protocol TCP. I might have made one mistake here, and I have. This is match any, and that just does not jibe with Flowspec. So let me pause the video and fix this. So there I've fixed that, and it's now match all, which is good. And then we need to describe a policy map. So policy map type PBR. This is going to be PM VPNv4. The class type traffic here is going to be CM VPNv4 telnet, and then the action is going to be drop. So essentially, nothing much different. This is exactly the same way you would create a policy map for your global traffic. Let's commit this config and see where the difference is going to be. The difference is going to be in the application of this policy map. So now I need to say Flowspec VRFA. So inside Flowspec, I am in VRFA. And in VRFA, for address family IPv4, now I can basically apply this service policy. So service policy type PBR, and it is going to be PM VPNv4. And let's commit this. So show run Flowspec. And if show run Flowspec, now you see there are policies at both levels. There are policies at global IPv4 and IPv6, and then we have a policy under the VRF for IPv4. So now let's see if this actually came into the BGP VPNv4 table. So do show BGP VPNv4 Flowspec. And it has not. And I think the main reason for that is we don't really have, let's see, show run router BGP. I think there would be one more thing that is needed here. I need to define that VRF inside BGP as well. So just like we defined that VRF in globally and in Flowspec, we need to define that VRF in BGP. Router BGP1, VRFA, which essentially might also mean we need a route distinguisher here. But I'll try to do it without the route distinguisher, and let's see what happens. We'll say address family IPv4 Flowspec, because remember, inside the VRF, it's just simple IPv4 Flowspec. I'll say commit, and it has failed. Show configuration fail, and like I said, you need an RD for this. So I'll follow my regular RD scheme, which is going to be 1: the device number. So 1:1 in this case. Let's say commit. And now let's say do show BGP VPNv4 Flowspec. And there's that route that we needed. So it is with a route distinguisher, just like you add a route distinguisher to a regular IPv4 route to create a VPNv4 route. We're doing the same thing here. If I look at the detail of this, so just copy that whole thing and paste it in here. Actually, I'll have to give an RD as well, because this is a VPNv4 route. So RD 1:1. And now we can see everything else is the same. So inside the route is the same. The only thing is it has been tagged with a route distinguisher. So now if you think about it, it made sense, right? We always needed the RD. Once we are done with that, let's go and check this on PE4 and PE6. Do show BGP IPv or VPNv4 Flowspec all. And there's that route, and it has been absorbed. So there's that route advertised from the route reflector. Here's the route with a massage route distinguisher. Actually, in the it has been adapted into VRFA. The same thing will happen for PE6, which is more important because that's where the device that we are trying to protect is. Now, it is still not complete. So let's try this. Let's make sure that it is not complete. See, this connection is still working. So this is still not complete because we still need to, even under the VRF, do the apply interface all command, right? So that command still doesn't go away. We'd only need it on PE6 in this case, so I'll only do it on PE6. So we'll say Flowspec, VRFA, address family IPv4, local install on all interfaces. I'll also do it for address family IPv6 because that's coming up. And now what should happen here is, well, it doesn't look like it's gone away. Actually, no. So that's the wrong device. PE6 is the, well, it's a VRF device, but really, remember, on Ingress only. So it makes sense that it's not stopping the traffic. It should have actually be on PE4. So let's cheat a little, do show history. Let's take all of this and copy it on PE4. Now what should happen is this should go away. So right now it's not responding, but once it completely let's check out the lines. I'll say disconnect 1. And let's recreate that connection now, and it should not respond. And what you should see in addition to that is in here, do show Flowspec VRFA. You should be able to see the same thing that we saw there. We should see packet matches. If I say detail, there you go. 30 packets went back and forth, and 30 of them were filtered on the ingress. So now quickly pausing the video, I'm going to create an IPv6 policy and then we are done. So very quickly, here are all of the changes that I've made on iOS XR. I've added address family IPv6 Flowspec with the right route targets to VRFA. I've created a class map that matches our traffic. Replicating IPv4, we have created a policy map that drops the traffic matched on that class. Under Flowspec VRFA address family IPv6, I've applied that policy map. Finally, in router BGP1, I've created address family IPv6 Flowspec in VRFA and committed the config. So that's all it takes. You can pause the video to go through the details of that. But now when I do show BGP IPv6 or VPNv6 Flowspec, I should see that route here. Not only here, I should see that route on PE4. Do show BGP VPNv6 Flowspec. All. There's that route. And finally, do show Flowspec VRFA IPv6 detail. So those packets are there. Now, we should not really be able to get to CE10 from CE9. So we'll say telnet. This is going to be 2001:10:10, and then source interface is going to be loopback 0. So it doesn't seem like that's happening on PE4. We should actually be catching those packets. And so we are. So we never verified that we were able to actually telnet in there, but you can see the traffic is being caught on the PE device. And that really brings us to the end of this demonstration. We obviously didn't do the very last part. Junos as a controller for either IPv6 Flowspec or VPNv4 or VPNv6 Flowspec, but the idea is fairly similar to everything else. That brings us to the end of this video, which really just scratches the surface of this very sophisticated tech. To unleash its true power, be sure to follow the links in the description box. As always, I hope you've enjoyed this video and are looking forward to the next one. Thanks.